Hello, dear students. Welcome you all. In today's lecture, we are going to start discussing the applications of Maxwell equations, right? Applications of Maxwell's relations, right? We have derived four Maxwell relations in the earlier lecture, and now we are going to start discussing the applications of these Maxwell relations. In the sequence of applications, the first application that we are going to discuss in this lecture is Clausius-Clapeyron relation. Right? Clausius-Clapeyron relation. This is the first application of Maxwell uh, relations. When we will drive this Clausius-Clapeyron relation, we will see what is the significance of this relation. So first of all, we will drive this relation. We will drive this relation by using Maxwell's second relation. Right? What was the Maxwell second relation? Curly S upon curly B at constant T, that should be equal to curly P upon curly T at constant B, right? So this was Maxwell's second relation, right? So the first thing that you have to remember, that while driving Clausius-Clapeyron relation, we are going to make the use of this Maxwell's second relation, right? Now, uh, if I multiply this equation 1 by temperature T on both the sides, right, then in this case it will become like this. Now I can take this T inside the bracket. So if I took this T inside the bracket, then it will become T curly S upon curly B T, that is equal to T into curly P upon curly T B, right? So here we can write curly S multiplied by T. It is just like a TdS, right? So according to the second law of thermodynamics, it should be equal to dq, means I can write here curly q. Clear? So in this equation, I am going to give this name as equation number 2. In equation number 2, I can substitute here this, right? So when you will substitute it, you will get uh, this relation curly q upon curly b t, that is equal to t into curly p upon curly t b. This is equation number 3, right? Now look at equation number 3, right? In the left hand side of this equation, we can see this term is representing the amount of heat curly q that is either evolved or absorbed, right, at constant temperature T, when the volume is also changing, right? Or we can say it is representing the amount of heat absorbed or evolved per unit volume at constant temperature T. What is this heat? Clear? When the temperature is constant, the system is either absorbing or evolving heat. So we give this heat as the name latent heat, right? Latent. Latent means hidden, right? The temperature of the system is not changing. It is constant. What either the heat is absorbed or evolved, right? With respect to the change in volume, right? You can take the example of melting of ice. When the ice is contained in a container, and if let this ice has the temperature minus 10 degree Celsius. Now let we are supplying heat to this container. So the ice is obviously going to convert into water. So what amount of heat we are supplying here, that is going to increase the temperature of the ice, and at 0 degree Celsius the ice will convert into water, right? So when the temperature reaches 0 degree Celsius, then at that temperature the heat supplied to this system will be utilized in changing the phase of this system, phase of this material, right? So the material inside this container, that is water, now it is changing from a solid to liquid, right? So the heat utilized in doing it is called latent heat, because the temperature is same, 0 degree Celsius. Temperature is not changing, but the state of the material is changing, right? We know the latent heat of water at 0 degree Celsius is 80 calorie per gram, right? This amount of heat, approximately 80 calorie per gram. This amount of heat is utilized in changing uh, water from solid to liquid phase, right? I mean from ice to water, right? So in this equation, this is the interpretation of this equation number 3, right? Now to make a even more broader, uh, you know, meaning of this equation, let's consider a material which changes its phase, like water, from solid to liquid or from liquid to vapor, right? At temperature T, temperature is constant, and the amount of heat absorbed or evolved is that is curly Q, that is latent heat. I am giving this as a name L, right? And curly V, we can see the initial volume was V, and the final volume is V initial and V final. Clear? So in this equation, we can put these values. So this will become L upon V initial minus, uh, sorry, V final, because V final will be more. So V final minus V initial, that is equal to T curly P upon curly T at. Clear? So if I simplify it further, then this equation will become now curly P upon curly T B, that is equal to L latent heat upon temperature T into V final minus V initial. Clear? This equation, clear? This equation, I'm going to give this name as equation number 4. Clear? Here, we can write in place of here. Now this curly P upon curly T will become saturated. Clear? When we are considering this condition. So I'm going to replace V with the word saturated. Clear? Right. So this equation is called Clausius-Clapeyron relation. Right? This is called Clausius-Clapeyron relation. We have derived this relation by making the use of Maxwell's second equation. Right? Now, what is the utility of this relation? Right? You can make the interpretation of this relation. Uh, from this relation, it is clear that the right hand side, clear, as V final is more than V initial, so it is positive. So it means curly P upon curly T saturated is positive. Clear? So it is clear from here that if it is positive, it means if the pressure is curly P, change in pressure is positive, change in temperature should be positive. It means, right, with the increase in pressure, the boiling point of the material should increase. Clear? Boiling point should increase with increase in pressure. Clear? If delta P is positive, then delta T should be positive in order to get this relation satisfied, because this is positive. So it is very important. We know when in case of a liquid, for example, in case of a water, clear? If we increase the pressure, then the boiling point of the water go on increasing. We have seen it in the case of a pressure cooker. If we cook the food inside the pressure cooker, we are going to supply heat from here. Water is contained inside the pressure cooker, right? And some food item is present along with the water, and we are supplying heat. Clear? So as we are supplying heat from here, the pressure inside the cooker is going to increase, because the water vapors that are becoming here steam, that is getting from the water, is not getting out from the air. So it is applying pressure back on the liquid, right? So the pressure of the water is going to increase continuously. So if the pressure is increasing, it means the temperature is also going to increase with the, obviously, but the boiling point, clear, boiling point is also going to increase. Why? Because the this, according to this relation, this has to be positive. So if the pressure increase, delta T is positive, means boiling point will also increase. So the water inside this pressure cooker will not boil, right? It will keep on acquiring the heat. Its temperature will continue to get rise with the rise in the pressure, but it will not boil. Clear? So this is the one example. You can have other example. Clear? If we took this pressure cooker on a very high hill, right? Then what will be there? Clear? Atmospheric pressure will be low, right? Atmospheric pressure will be low. On for example, let's take the Mount Everest. Clear? So the air pressure is very low. So air pressure is low, it means when we are doing this experiment there, right, when we are hitting it, clear, we can see here. So suppose initially this pressure cooker, when it is on the Mount Everest, it was, open. Clear? It was not closed. There is a water inside it with some food item, and we are going to supply heat. Right? What will be the effect there? The water will start boiling even at very low temperature, not 100 degrees Celsius, but it will be obviously less than 100 degrees Celsius, because here in case of Mount Everest, the atmospheric pressure is very low, air is very rare, right? We know any liquid start boiling when its vapor pressure becomes equal to the atmospheric pressure. But here the atmospheric pressure is low, so this liquid will start boiling at a temperature lower than 100 degrees Celsius when this is open. But what will happen when we close this pressure cooker, right? We apply the cover of this pressure cooker to it, and then we start heating it. Again, what will be the effect? Again, the same thing. Now the boiling point will increase, because we are applying artificial pressure here. clear, of the steam. The steam that is coming from the heated water is applying pressure on the water, right? So it means now it will take more amount of heat to reach at the boiling point, right? The same thing with the application of pressure, the boiling point will go on increasing. So this is the interpretation of this Clausius-Clapeyron relation, right? So this is all about it. We have seen that we have derived this Clausius-Clapeyron relation by using Maxwell's second relation, right? We took it, this is question number 1, we multiplied on both the sides with temperature, clear? Then we took T inside the bracket. According to second law of thermodynamics, we have used here. Then after simplification, we got this relation. We further modified it and we arrived at equation number 4, which is called Clausius-Clapeyron relation, right? We have seen what is the implication or meaning of this relation. What is the utility of this relation? So this is all about this relation. Thank you very much.